Awesome. Thank you so much, Susan, for such a wonderful introduction, and Nasreen for an amazing talk to already motivate what I'm going to talk about. So I thought that since I'm a theorist myself, like the first thing I wanted to understand was, okay, this large language models are everywhere. What are they actually doing? Like at the bottom, like just opening up this black box and understanding, like right below the surface, what is actually happening. And I thought I would share some of this. Maybe it'll be a little bit more technical than what you're expecting, but hopefully it'll help you understand what's going on and maybe get some technical tidbits that you can use in your day-to-day life. Okay, so feel free to ask me any questions. If something doesn't seem easy to understand, just raise your hands and I'll try to answer those questions while we go forward. Okay, so let me start with, just showing you all these articles that, I just had to like go on Google News, search ChatGPT or AI, and you can find like hundreds and hundreds of articles talking about these models. And these are articles that talk all about like excitement of what AI is being used for. For example, that they've entered our classrooms, they've entered lawyers and doctors, and they're being used in all these real-world applications. Whereas there are also these articles that you'll see that, okay, it's becoming very, very active, but unfortunately, even though it's really active, it has its own issues. Like, for example, this article that even ChatGPT says ChatGPT is racially biased. Yeah, and ChatGPT may hallucinate more often than you realize, and in fact, it has even one wrong answer lost Microsoft a lot of money. Just because ChatGPT produced a wrong answer. So, and even more like the governments are getting involved in this, right? Biden issued an executive order to create AI safeguards. And all this to say that AI even got named as the most notable word of 2023. So this is something that's like become so omnipresent everywhere that this is all everybody's talking about. I remember like 2 years ago, I would go to a restaurant in New York and people would be talking about, what's the new movie to watch, what is the new book to read. And today when you go around, you'll just hear somebody talking about what is the new AGI application or where have they used ChatGPT in their life. So this is something that's become so notable that it's like worthwhile actually understanding what it is really. So when I say a large language model, like one thing that'll come to your head is going to be, these different language models that you interact with, ChatGPT, Gemini, Llama. How many of you have heard of Llama? Okay, good. There's a new one that Amazon has come out with, which I didn't have the time to put in. I think it's called Smog. So there are all these language models that you hear about, and what you think of them are this interface that, say, I'm talking to this interface. Here, I just asked, this model to write the abstract of the talk that I put in. And it gave me like a nice summary and a nice conversational thing to give me what this abstract would be. So the way we think of it is like we're communicating with this model in this language format. But what is really a language model is something that we forget, and it's something that's a really simple mathematical concept of what a language model is. Okay, somehow Nasreen and I both decided to go with animals eating food. So here now we talk about mouses eating cheese. So this is going to be a line that you'll see all throughout the talk. Very simple concept of a mouse eating cheese. Okay, so we'll think of a language model. Right now I'm cutting out the large part of it. Okay, so this is just a language model. We'll put back the large at the end of it. So a language model is a really simple model that does something very simple. It takes every sentence. You can think of a sentence. Right now I'm looking at the abstraction of a sentence, but you could think of a paragraph, a book, and assigns the probability of how likely the sentence is in language. Okay, so for example, here I just put an abstract number that the probability that the mouse ate cheese being a valid sentence is 0.001. And more generally, you can write this as a probability of any sentence, and when we abstract this out, we put them as tokens, so you can think of these as words, W1 to WK, and this is just assigning a probability to this sentence. So let's think about what this really means. So a higher probability would mean that this is a good sequence, this is a likely sequence, right? So one thing that you could imagine that it captures is syntactic correctness. So if I gave a sentence such as the mouse ate cheese, what would you think? This is highly unlikely, right? So what would you want your model to output? A very, very low probability to this sentence, right? So this is an example of syntactic correctness. Something else that a probability model, like a language model, would capture is world knowledge. So supposing I have this, the mouse ate cheese, I actually did the arrows incorrectly. So the mouse ate cheese should have a much higher probability than the cheese ate mouse, right? Because this is a concept that you know that a cheese cannot probably eat mouse, but a mouse can eat cheese. So the language model is just an abstraction that tries to estimate these probabilities so that we have an idea of both syntactic correctness and word knowledge captured in this language model. Okay, so now I told you what a language model is. It's a probability distribution. But what we were talking about before was this interactive, generative thing that we were talking with it. What does a probability distribution have to do with that, right? So how do we actually use this probability distribution to get this word-by-word interaction that you do with ChatGPT in the following sense? Okay, so what you can do is you can just start with, supposing I want to generate this sentence, and this is a very idealized world, and I have only these 5 different words that I could generate from. So initially, I could start with this probability that all of these words are equally likely. I could sample a sample from here, and maybe I get the word the. Okay, now that I have this, what do I want to do? I want to generate the next possible word from here. So now once I take the probability that I have seen the, some words are more likely, and some words are less likely in my model distribution, right? So for example, after the, I don't expect another the. So this has very low probability. I don't expect another 8. Maybe I expect one of these nouns to follow. So then I can sample again from this new distribution. I can get maybe the mouse. Then I can do this again. Once I have the mouse, the only thing that seems that would fit really well is going to be 8 here. And I can sample again, and I can get 8, and so forth. I can get the sentence. And I can keep doing this. As long as I have a probability distribution underlying, I can keep sampling as many characters that I want. And underneath your language model, this is how the sampling is actually happening to generate your sentence. Okay, how many of you seen language modeling before? Okay, great. I see a lot of raised hands. This is actually not new. People have been doing this forever. The oldest model, the n-gram model, exists from like 1950s. And as Nazreen had also pointed out, the perceptron algorithm is from around the same age. And this is a really simple idea that if I really wanted to estimate this probability distribution, what would I do? I would just look at the last few tokens and try to find what is the most likely token that I could fit in after that. Right? It's a very simple idea. So for example here, if I gave you this entire sentence, I could just look at mouse 8, and what would you fill in after this? Maybe cheese. That's the most likely thing that you think of. Maybe some fruit, maybe some grain. But you would just put in a word here. Okay, this is known as the n-gram model. And it looks at the last n-1 tokens, and it just generates the next token. Now, can somebody tell me why would this be a bad idea? Yeah.
It doesn't take into account context.
Exactly. So, you know, I said something here. The mouse was craving something creamy, so the mouse ate dash. And when I looked at only the last few words, I didn't actually notice this creamy word at all. So I could output a fruit, and that would not make any sense, right? So one thing that was wrong with this model was that if you wanted to actually get a lot of context, you would have to look at a lot of tokens behind. And if you had to look at a lot of tokens behind, you would need a lot of data to even find such a sentence that happens in your data. And this, so taking something really small actually does not capture all these large dependencies that you might have in actual language models. Right? Actual language has a lot of dependency, and we wouldn't be able to capture. So this idea, even though it was a very classical idea, did not really work well when we wanted to generate more complex data. So what did we do new? What is a new idea that came about with these large language models that actually changed this whole problem? So what we did instead was instead of like estimating the probability by just counting how many times things occur, we instead were like, okay, we know these neural networks work really well. Why not put a neural network on top of this and try to estimate the probability using a neural network? Now we can feed the entire sentence to the neural network and ask it to just generate the output. And the main thing that came about new, which you might have heard, you must have heard this paper before, this title, Attention is All You Need, was this new model of the neural network, which is called the transformer. And this new model just took this new concept called attention. It's also not new, to be honest. It's from the early 2010s. But it took this concept and combined it with the standard neural networks that existed and put this as the probability computing element. And once it put this in and we estimated this probability, these models started doing really well. Okay, so how many of you had heard of transformers before? Okay, great. So a lot of you have heard of transformers. How many of you know what a transformer is? Okay, I see a couple of hands. Okay, so I'm going to give you a very, very, very quick basic introduction of what a transformer architecture is. So maybe next time you talk to your friends, you can tell them you know what a transformer is. Okay, so what does this transformer do? I'm going to go again with this example of the mouse 8. I'm going to try to predict the next word cheese, so I'm going to just have this mouse 8 so far. Okay, so what is this idea of attention? It's trying to handle this issue that we had with our n-gram model, which was like the n-gram model was only looking at a few tokens before that, and it didn't know how to look somewhere really far away. So what this attention does is that it tries to create a way to look back as far as you want and pick out what are the words that are really important. So you can think of it as like a pointer that's just looking behind and trying to find what is most relevant to this word 8 that I can use to generate the next word. Okay, so what it does is, this is going to be slightly more technical, but bear with me. What you're going to do is you're going to take these words. Operating with words is very complicated, so in most of computer science, the way we think about it, we map these words into something that makes sense to us, and mostly these are vectors. So what we do here is that we take all these words, we embed it into some vectors. So just think of these as just some objects that represent the mouse and the mouse and 8. Okay? So this is the first step that the attention mechanism does. It just takes the words, embeds it into a new dimension. Okay? Then what it does is it embeds this token into three quantities. This will seem very familiar if you've looked at databases. It's going to embed it into a property called key, a property called query, and a property called value. Okay, so it's going to just take this vector and make 3 more vectors out of it: the key, the query, and value. Okay, so once you have the key, query, and value, what does this model do? I want to figure out what I want to do with the word 8, so I'm going to take 8 as the query. So this is the query that I'm taking, and I'm going to take all the different other words and try to take this query and query how related the other words are. So I'm going to take this query here and multiply it with all the keys of the different tokens. Okay, so what I did was I took this query and I'm like, I'll ask the mouse, how much does this word relate to you? I'll ask how much does this word relate to you? And I'll get some scores. And all I'm going to do is take these scores and make them into some normalized values that assign like, oh, okay, 10% I care about 8, maybe 50% I care about the word mouse, and 10% I care about the word 8. So I'm going to get this distribution, and what I'm going to do is just take the values now, combine these with these weights, and output a new embedding 8. So once I've done this, what has this word done? What has this whole attention mechanism done? It's taken these words, it's taken my current word, computed some score of how much my word depends on these other words, and averaged that to get a new embedding. Now that new embedding has information of how much 8 relates to mouse and the. Before that, it didn't know anything about this. Okay, and now that I know that 8 depends a lot on mouse, maybe now when I have to generate the next word from 8, I can be like, oh, mouse, what does mouse eat? If my knowledge base has that, I would say eat cheese. So this is what the attention mechanism does, and like I said, it's like basically like a pointer into the rest of the context. So this I'm just showing for 3 words. You could imagine there would be like 100,000 words it could look at and decide how much it needs to weight each of them and combine it. So what is a transformer? It's actually a really simple idea. You just take attention, you add a standard neural network, you create this, and then you repeat it a bunch of times. You just keep repeating it so that you keep doing this attention mechanism many, many times, and you get your transformer model. And that's all that's happening inside. When I parameterize my probability distribution, I put this transformer into it. Now you're going to ask me, how do I actually learn this probability distribution? I just told you this architecture. It's some architecture. How do I actually learn it? And actually, the idea is pretty simple. You just train this transformer to predict the next token in your sentence. We have a lot of text. Like, think about a Wikipedia article. This is a Wikipedia article about WiDS. I can just take that, and I can try to predict the next token. So for instance, I can start from founded in 2015 and ask it to predict at, and then ask it to predict the next word, Stanford, and so on. And if it is able to predict this, then it's actually able to do a lot of things that I wanted my probability distribution to do. Remember, I wanted it to be able to parse syntactic text structure really well. So for example, if it has to predict these underlying words, it has to learn how to parse syntactic text structure. It has to learn how to perform factual inference. For example, if it has to predict Stanford University, it needs to know that WiDS was founded in Stanford University, right? And it has to retrieve these associations, right? It needs to know who founded that. So it needs to store somewhere who founded WiDS, and so on. So only this next token prediction task can actually generate you a lot of interesting data already of the world models. So just predicting the next token is actually very powerful, and we can basically just train this model and learn the probability distribution that we wanted before. And that's what's happening underneath. Now let me add the large back to it, because this is where the large language models and that came into power, right? So let's talk about what a large transformer is, a large language model is. It's basically a large transformer trained on a large amount of data with a large amount of compute. So for reference, I'm going to ask you all, what do you think the sizes are going to be? So let's think of compute in terms of hours per your computer machine that you use. How many hours do you think a GPT-3 model would have taken? Any guesses?
Can you repeat the question?
So think about your ChatGPT model that you're using right now. How much compute could have it used in terms of hours of computer on your basic laptop, for instance? 1 hour of compute on your basic laptop. 100,000? Billion. OK, great. So actually, if you count it as 1 hour of laptop, it's 999,000 years of compute that you actually need to use for this.
Did you say years?
Yeah, years. Years. Not hours, years. For data set size, this is even more interesting. If you consider a bookshelf of 100 books, you actually need 30,000 bookshelves of data to actually run this model. That's a lot of bookshelves. Probably none of us is actually reading in our lifetime. And the most interesting one for parameters, if you think of 1 centimeter as 1 centimeter, this small piece as 1 parameter, it is actually 2,500 soccer fields worth of parameters that this model actually relies on. So this is where the large actually fits into this entire picture. OK, so it's really, really massive. I really like this visualization, which is from Anil George, that actually puts in perspective, how large these models are. Sometimes when somebody tells you billions of parameters, you're not able to wrap your head around this. But this is a really good way to see how large this model is. And once it's large, you can see that actually making it larger seems to help a lot. So as large as you make it, these models get bigger. So whatever sizes I put here, GPT-4, the current model, is actually almost 10 to 100 times bigger than even this. OK, so it's gigantic. And it seems to help with performance. And in fact, they start to do a lot of cool stuff. This is a stat of how they pass like a lot of the SAT exams, bar exams, GRE, all these exams that you might have in some point in your life maybe taken. These models are actually getting pretty good at it. And in fact, they're able to even do things that are like more creative than you would expect, like writing poems on proving the infinitude of primes, drawing a unicorn in LaTeX. And maybe these are like fun applications but not useful. But coding, I guess, is the most useful application that they have actually been very involved in. And so they were not trained on these tasks. Like what I told you, they were actually trained on next word prediction. And they were able to emerge with all these amazing reasoning capabilities. And I'm going to end with saying that this is not it, right? Do you think this is it? Are we done? And I guess Nasreen already pointed out that we're not really. Like, they're not actually solving a lot of things. And in fact, if you play around with them, they can't do basic addition. They understand who's Tom Cruise's mother. But if you ask who is that mother's son, they can't answer that question. And in fact, their giving wrong answers actually causes a lot of issues to these companies. So these are called hallucinations. Even worse, they can be attacked. You can come up with one string that you can add to all the language models, and you can completely subvert all their guardrails that they have in place, and you can ask them to generate really things that you don't want these models to generate. So this is a very simple example of asking asking the model to tell you how to write social media posts that encourage people to do dangerous things. But you could imagine the other examples people have shown is like how to create a bomb, how to do all these sort of things that the model should not output. And even worse, that probably all of us have experienced in our personal life, these models actually are very biased. So if you ask them to generate data for a woman, they will use words that are very different from generating data for a man. So there are a lot of issues that these models still have, despite all the progress that's been made. And my research, actually, this is all the introduction to the models. I wanted to end with saying that what my research tries to do is to try to understand how they actually think. So my research focuses on taking these complicated models, looking at them the way I explained to you, very simplified, what actually is happening in the model, and try to create simplified setups which replicate these behaviors of large language models, allow for control, and are amenable to math, and try to understand what's actually going on. And I truly believe that understanding how these actually work internally is very crucial to improving the reliability. So if you don't understand what the model is doing, we really can't improve the model. And I'll just give you an end with one simple example of a research project that I can just explain by pictures that we came up with. We tried to understand how our LLMs think, and we showed that they think in a very parallel way. And what I mean is that if I ask you this task, it's a very simple cognitive task where you just have to tell me if these two patterns are actually the same. One way that you could do this, which many algorithms would do, you would start from the left, and you would keep checking each position and try to see whether actually, oh, this is green, that's green, okay, this is good. Green, green, good, red, red, and so forth. This is an iterative solution, but many of you would actually not solve it this way. What you would solve is you just abstract your head and look at only the green color, or you look at the orange color and match that roughly this looks the same. And this is a very parallel solution because you looked at each color, not at each bit, because humans can do this really fast. And our research actually showed that transformers also learn these kind of solutions instead of this kind of solutions that you expect a normal algorithms to do. And I'm going to end here. And if you want to learn more about my work, come chat with me. I'll be around most of the day. And I'd be happy to tell you more about how we are trying to understand these models. Thank you so much.